Now that we know how to identify if a compound is going to be named under ionic naming or molecular naming, let's go ahead and practice and learn some of the stuff we need before we can actually practice the ionic naming. So ionic compounds, again, ionic are made up of cations and anions. So a cation, which is positively charged, pairs up with an anion, which is negatively charged. The thing about ionic compounds is we're not going to use prefixes. So do not use number prefixes. We do that in molecular naming. We use prefixes to emphasize or to clearly state how many of each type of species or atom we have in the compound. We don't do that for ionic compounds, though. We instead can use the formula to derive the charge or use the name to derive the charge, whichever way we're going. And you need to be able to do that. So first up, we need to talk a little bit about some monatomic cation. Monatomic means it only forms one charge. And meaning it only loses, for metals, they only lose one set of electrons. Okay. So uh, polyatomics have set charges. We'll talk about polyatomics a little bit. But when it comes to your metals, remember your metals can form cations. So cations can either be a metal ion or a polyatomic. Anions can either be a nonmetal ion or a polyatomic. So for the metals that are forming those cations, they have fixed charges. Some of them do. And it says here from main group elements. So groups 1 and 2, aluminum, silver, zinc, cadmium does this as well. You need to know these charges. This is the atom, an atom name. This is the ion, and this is the ion name in a compound. And I've said what I mean by that in just a sec. But if I just have an atom of sodium, I just call that sodium, okay? But if I form a sodium ion, sodium is in group 1. Group 1 is your alkali metals. Group 1, no exceptions, always forms a +1 charge. They always lose 1 electron. But if I have Na plus, where it's actually lost that 1 electron, this is called a sodium ion by itself. It is not just a sodium by itself. You just say sodium, I'm assuming you mean a neutral atom. Sodium ion is Na plus. In a name, I call that sodium. So like when you say sodium chloride for table salt. Notice that first name is just still the name of the atom, but I can tell it's an ion because it's in a compound. Second one listed here, calcium. Ca is calcium. And notice that calcium is part of group 2. Group 2 is your alkaline earth metals. Group 2 species always form a +2 charge, no exception. They will lose 2 electrons. So if it's in the ionic form, I do call this a calcium ion. But in a name, I just call it calcium. So I would call it like calcium chloride. Because it's in the name of ionic compound, I know it's an ion to form that. We also have aluminum that has a fixed charge. Aluminum is in your P block. So when you're looking at your periodic table, you've got groups 1 and 2 over here. We're going to pretend these are boxes. You got your P block over here, and then you got your F block down here, okay? So groups 1 and 2 are here. This is our P block over here. This is our transition metals over here. It's our F block down here, but aluminum's over here. We're going to see this a little bit better on a periodic table on the next slide. Aluminum's right here, zinc is right here, silver's right here, and cadmium's right here. Aluminum Again, Al is its atomic symbol, and we just call it aluminum. But if I have the aluminum ion in a name, I still just call it aluminum. So like aluminum chloride. If I have the ion by itself, I'm calling it aluminum ion. Al3 plus is the aluminum ion, but in a compound, it's just called aluminum. Aluminum, no exceptions, has a +3 charge to it. So group 1, alkaline metals, always +1. Group 2, alkaline earth metals, always +2. Aluminum, always +3. The other ones you need to know are zinc and cadmium, are always +2, no exceptions. They are in your transition metal block. And silver's always +1, no exceptions. We will learn soon why this happens, like why we see this happening in just a couple chapters. But for right now, you just need to memorize it. So looking at the actual periodic table with it, again, your alkali metals, all +1 charge. Your alkaline earth metals, all +2 charge. We'll talk about your nonmetals in just a minute, but let's talk about these here. My aluminum, +3. My zinc, +2. My silver, +1. That's how I remembered it. I stepped down 3, 2, 1. Okay. Aluminum here, 3. Zinc down 2. Silver down 1. And then cadmium fits in really nicely right here at a +2 as well. So you have to know those. Now, on the next slide, I will show you your nonmetals, but really everyone wants to be like a noble gas. Everyone wants electron configuration just like a noble gas, which is, again, a future chapter. We'll talk about it. If our alkaline earth metals can lose 1 electron, they can be just like the noble gas that precedes them. So these can all, sorry, hydrogen is not in metal, but hydrogen can either, hydrogen is right here. Hydrogen can lose 1 electron very, very easily. We call it a proton. Or it can gain 1 electron, and we call it hydride. And the name will make sense when we talk about the names and the metals in just a sec. But notice here, my halogens, all -1 charge. Oxygen's family, all -2. Nitrogen's family, -3. And that's because it's 1 spot, 2 spots, and 3 spots to get to the noble gases. They want the same electric configuration. Halogens jump 1 spot, and they can be just like a noble gas. They form a -1 charge. Oxygen's family, 1, 2 spots to reach the noble gases. They have a -2 charge. Nitrogen's family, 1, 2, 3 spots, -3 charge, and they're just like a noble gas now. Any of the other metals, the metals in here, the metals under here, you can get their charges from their names or from their formulas. So again, naming anions, Cl is called chlorine. It's a chlorine atom. Okay, if I have Cl minus, it's called a chloride ion. Notice in metals, we did not change the name at all, but in anions, we changed the ending of the name. IDE. So chlorine becomes chloride. Oxygen becomes oxide. Nitrogen becomes nitride. We dropped the end of the name and added IDE to it. Again, oxygen's family, group 16, always -2 charge. Nitrogen's family, group 15, always -3. Halogens, always -1. So transition metals and some of your metals that are in the P block that are not technically transition metals, you have variable charge states or variable oxidation states. Oxidation is how many electrons it can gain or lose. In the case of a metal, it's lost. This can be variable, it can change. So we see here a few different examples, iron, copper, and gold, where they each have 2 different options. Notice here we've got 2 different naming conventions. We've got ferrous and ferric versus iron 2 and iron 3. Cuprous and cupric versus copper 1, copper 2. Okay. The us and ick naming is the old style convention. Us means the lower oxidation state, so the lower plus charge. Ick meant the higher. You need to be able to recognize these names because you will see them on older chemical bottles. So you will see things like ferric chloride, and you need to realize that that means iron 3 plus. The hard part with that naming convention is that you have to know what charges those metals will form in order to name them properly. So personally, I find it easier for my students just to use the Roman numerals, but you should be able to recognize the other ones. So again, iron likes to be plus 2 or plus 3, so it forms ferrous or ferric. Copper likes to be plus 1 or plus 2, it forms cuprous and cupric, but notice the difference between here. For iron, ferrous is plus 2. For copper, its plus 2 is ferric, or is cupric. I apologize, cupric for copper. That's why this gets confusing, okay? You should be able to recognize them, but I recommend most students focus on the Roman numeral naming because I think it's more beneficial for students and it's more currently used. You'll see this on older bottles. The Roman numeral numbering is where the Roman numeral tells you the charge of the species. So this is iron 2, which means iron plus 2. This says iron 3, which means iron plus 3. Copper 1 means copper plus 1. Copper 2, copper plus 2. Gold 1, gold plus 1. Gold 3, gold plus 3. Chromium 6, chromium plus 6. Okay, I find most of my students have better luck using the Roman numerals, and that will be sufficient for what you guys need. You should be able to recognize the us and ick though, and be able to, like, if I tell you, if I had said, iron has a plus 2 charge and a plus 3 charge, which one's ferric and which one's ferrous, you guys should be able to tell me that. Okay, your polyatomics. You just got to memorize these. There's no way around it. There's no ifs, ands, or buts. Memorize them fast. You're going to be using them all year long. First ones up are plus 1 charge: ammonium, hydronium, and mercury. Okay, ammonium comes from ammonia. You will be using ammonia in a future semester. Ammonia is NH3, it is a base. It looks like this in its Lewis structure. Lewis structure is just a simple two-dimensional way of connecting the atoms. So this is ammonia. You don't need to know that quite yet, but that will be coming, okay? Ammonium is where I take that compound and I give it a proton. So I don't give it any more electrons, but I give it a proton. This causes the overall species to have a plus 1 charge because now there is a bond here where that nitrogen gave up its electrons to form that bond. Ammonium is one of your few positively charged polyatomics. Hydronium comes from water gaining a proton. So this is nitrogen gaining a proton. This is water gaining a proton. Again, this is just the Lewis structure of water, which is not the actual 3D array of the compound, but this picks up 1 proton. So that donates that pair of electrons to form a bond there, forming hydronium. You are not responsible for drawing these yet. Okay, that will come in a future chapter. But sometimes for some students, drawing them out helps them see the structure a little bit better. H3O plus. Mercury 1 is a polyatomic. It is mercury 1, so I have 2 mercuries here at a plus 2 charge. So each mercury has, it's like the equivalent of each mercury having a plus 1 charge, but it is a polyatomic. So if I say mercury 1, I mean Hg2 2 plus. Cyanide, Cn minus. Notice cyanide versus cyanate. The difference is the ending. Ide to ate, I've added an oxygen here. So cyanide to cyanate has the same charge, but the Cn minus has gained an oxygen atom in the compound as well. Thiocyanate, thiol means sulfur. So I replaced the oxygen with a sulfur. Hydroxide, you guys need to know. Most common base that you're going to see in general chemistry, strongest base that can actually exist in aqueous solution. Hydronium is the strongest acid that can exist in aqueous solution. You just need to know those. You're going to see them all the time. Acetate, you're going to see drawn both ways. I tend to draw it this way, which is the way it's connected. It's the organic way of drawing it, organic chemistry way. So it's the way the molecules are actually connected. A lot of you will draw it the shorthand way, which is completely fine. I recognize the shorthand way. I just don't draw it as fast. So I don't think about it. But you should be able to draw it you should be able to recognize both ways, but be able to write it out either way. Azide, N3 minus. Do not mix this up with nitride, which is N charged 3 minus. This means 3 nitrogens, -1 charge. Whereas this one means 1 nitrogen, -3 charge. Got nitrogen in the table, we make that an anion, we give it a -3 charge, and the ending of the name becomes nitride. Don't mix up nitride and azide. Permanganate, MnO4 minus. Nitrate and nitrite, they have a -1 charge. You're going to see in a minute chlorate and chlorite also have a -1 charge. So people are going to mix up nitrates, carbonates, sulfates. There's a few different things you're going to mix up here, and you got to be careful about that. Nitrate and then chlorate. See if I can. There you go. Nitrate and chlorate have a very similar structure. Okay. So again, nitrate and chlorate have a very similar structure. One of the atom that it's starting the name of, 3 oxygens and a negative charge. And if I zoom out a little bit, we see here it says bromo-iota derivatives as well. What that means is bromate, BrO3 minus, and iodate, IO3 minus, have a similar structure. So nitrate, chlorate, bromate, iodate, okay? They all have one of their species and then 3 oxygens with a -1 charge. When you go from ate to ite, you lose 1 oxygen, but keep charge. Keep the same charge. So ate to ite, I lose 1 oxygen, I keep the same charge. And I'm going to see that pattern come up again. So nitrate and nitrite, NO3 minus versus NO2 minus. I'll talk about phosphates in just a minute. Carbonates and sulfates as well. Let's go down here and do the rest of the chlorates. So chlorate, bromate, and iodate follow these same patterns. BrO2 minus, IO2 minus. I do have these on another slide as well. BrO minus, IO minus, BrO4 minus, and IO4 minus. Okay. So chlorate to chlorite, ate to ite, no matter what it is, ate to ite. We lose an oxygen, keep charge. Notice though, if I go 8 and I add an oxygen, but keep the charge. I go from 8 and I add per at the start of the compound to per 8. So instead of chlorate, I have perchlorate. All I've done is add an oxygen, but I've kept the same charge. If I go ite and lose 1 more oxygen, but keep the same charge, I add the word hypo at the front. So hypo, and then ite still at the end. So hypochlorite. Some of you may have heard of hypochlorite. It's the active ingredient in bleach. So again, if you know chlorate, you know chlorite. If you know chlorite, you know hypochlorite. If you know chlorate, you know perchlorate. If you know chlorate, you know nitrate, you know nitrite. See the patterns here? Okay, it's all about the difference of an oxygen, but they're keeping the same charge. Now I said I'd come back to the phosphates and the carbonates, and the sulfates, and I will do that. But first, let's talk about these up here. Peroxide, just need to know peroxide. Phthalate, just know it. C8H4O4 2 minus. Okay, you're in the -2 charges now. Chromate to dichromate. Chromate, CrO4 minus, is very similar to sulfate, which we'll talk about in a sec. Sulfate is SO4 2 minus, and chromate's like that. It's got 4 oxygens attached to it. Sulfate is very, very similar. Okay. Now, dichromate means I've basically just doubled the compound, but it still has to hang out together. So where this is chromate, dichromate, dichromate is 2 of these, but they're going to be connected by that center oxygen. So now I've got 7 oxygens instead of 4. So some students will mix it up and try to say 8 oxygens. Can't do that because they still have to bond together. They have to hang out together, and there are rules that go into the way things can bond. But I did double my chromates, and then basically I took 2 chromate atoms and shoved them together. It's just that they're held together by 1 oxygen atom, not the original 2. So chromate, dichromate both have a -2 charge. Sulfate also has a -2 charge. But you can see CrO4 2 minus versus Cr2O7 2 minus. Again, I'll talk about phosphates in a sec. Okay, let's talk about carbonate. Carbonate is CO3 2 minus. So it's like nitrate, except it has a -2 charge instead of a -1 charge. Carbonate has a structure like this. Again, you're not responsible for these yet, but we will be soon. And if you put the lone pairs in here, which takes some time, carbonate looks like this. Now, if I have hydrogen carbonate, that means I gave this compound one hydrogen. So that's like doing this, okay? Hydrogen carbonate. It's the carbonate atom, but I've given it one proton. The charge goes down by one because I didn't give it a true hydrogen. I gave it a proton. I gave it a hydrogen ion, a hydrogen cation specifically. Hydrogen species that's positively charged. So it's also called bicarbonate, which most of you have probably heard about because that's what's in baking soda is sodium bicarbonate. What I've done is I've taken the carbonate atom and I've given it an H plus, which allowed the charge to go down by one, but puts an H in front. Sulfate, I know I talked about a little bit above, but sulfate, sulfur with 4 oxygens and a 2 negative charge. So 8 to 8, same kind of pattern. I lost 1 oxygen, keep the same charge. But like we saw with carbonate, anytime you have something that has a +2 charge or greater, it can pick up hydrogens one at a time, and we name them accordingly. So sulfate picking up 1 hydrogen would be hydrogen sulfate. We can also call this bisulfate. Sulfite picking up 1 hydrogen would be hydrogen sulfite. Again, we can also call this bisulfite. Now, we don't give like this compound, sorry, we don't give this compound 2 hydrogens because then it forms a different compound that we will talk about in a different chapter, but then it becomes an acid, so we'll talk about that in a future chapter. Thiosulfate is just like taking your sulfate, okay? So you take your sulfate ion, but thio again means sulfur, and I just replace one of these with a sulfur. And there's resonance stabilization happening in this compound. So there's reasons that this thing holds together. But same charge, I just replaced one sulfur with a thiol group with another sulfur group. Let's see, hydride. Again, hydride, most students forget that this can happen, but hydrogen is a nonmetal, so it can just pick up an electron. And then we just name it by name of regular rules. Hydrogen becomes hydride. Okay, -3 charge. We've got phosphate versus phosphite. Phosphate, you have to know is PO4 3 minus. Okay, structurally, it looks like this. And then you've got your lone pairs that I keep neglecting to draw in. But it's a 3 minus charge. Phosphite, so 8 to 8, same thing, lost an oxygen, kept charge. Phosphate is highly charged though, so it's greater than 1 is considered highly charged. So I can give it 1 hydrogen or 1 H plus, so the charge goes down by 1. HPO4 2 minus is hydrogen phosphate, or I could give it 2 hydrogens, dihydrogen phosphate. I don't call this biphosphate for the simple fact that I can give it more than 1 hydrogen. So hydrogen phosphate means I gave that phosphate group 1 H plus charge. We put 1 hydrogen in front and lower the charge by 1. Dihydrogen phosphate means I gave it 2 hydrogens and I lower the charge by 2. We see arsenate and arsenite, same style as phosphate and phosphite. Arsenic is below phosphorus in the periodic table, so it shouldn't surprise us that it has a similar structure. So arsenate, ASO4 3 minus versus arsenite, ASO3 3 minus. And then you've got borate here, borate BO3 3 minus. So similar style um, to the ites here. You just have to know that borate has just 3 oxygens and a 3 minus charge. Then carbide and silicate. Carbide should just come naturally from the periodic table. If you take carbon and give it enough electrons to be like a noble gas, it would be C4 minus. So I changed the name to carbide. But then silicate is one more that you guys should know. Silicate comes up in a lot of materials chemistry, SiO4 4 minus. Again, a lot of memorization here. You just got to memorize them. There's no way around that. Okay. So again, just kind of going back through those hydrogen and bi in the place of hydrogen words that I was talking about, you can create a new polyatomic anion by adding H plus to a highly charged. Highly charged means -2 or -3. I know it doesn't sound very high to you, but for these species it is. It means it's gained at least two, it's got at least 2 extra electrons or 3. However the compound came together, it's negatively charged. So again, sulfate becomes, if I give it 1 proton, 1 H plus, and again, this is a proton because hydrogen had 1 electron, 1 proton, but I lost my electron. So all that's left is 1 proton. I can either call this hydrogen sulfate or I can call it bisulfate. Either one is acceptable. They mean the same thing. CO3 2 minus is my carbonate. HCO3 minus, bicarbonate or hydrogen carbonate. SO3 2 minus, sulfate to sulfite. Give it 1 proton, bisulfite and hydrogen sulfite. And then phosphate, my PO4 3 minus. If I give it 1 hydrogen, I just call it hydrogen phosphate. If I give it 2 hydrogens, call it dihydrogen phosphate. Again, be careful. I am saying hydrogens because that's the way it looks in the formula, but you're really giving it the hydrogen ions or the proton there. And here's what I promised you guys, a little bit more just on the chlorate, bromate, iodate system, just after the name's actually written out. So again, this follows the same patterns as like nitrate, NO3 minus nitrate, ClO3 minus chlorate. Okay, they both have the -1 charge to them. So if you can remember chlorate, you should be able to do this whole table. Chlorate, bromate is just like it, BrO3 minus. Iodate is just like it, IO3 minus. All I've done is replace the element, the halogen in the species. 8 to ite, lose an oxygen, keep the same charge. 8 to ite, lose an oxygen, keep the same charge. 8 to ite, lose an oxygen, keep the same charge. 8 to per 8, gain an oxygen, keep the same charge. 8 to per 8, gain an oxygen, keep the same charge. And 8 to per 8, gain an oxygen, keep the same charge. Ite to hypoite, lose 1 more oxygen, keep the same charge. Ite to hypoite, lose 1 oxygen, keep the same charge. And ite to hypoite, lose an oxygen, keep the same charge. Okay, so there is a pattern to the polyatomics, but you have to get them down. You have to learn them.